Well, everybody, Mathman here, and we're going to take a look at our next topic, which is limits. Now, we introduced the idea of limits, where we look at the behavior of functions under certain extreme conditions or conditions in which create problems that arise, such as division by zero, and we know that that is something that just can't be. That a division by zero is undefined. It's something that is meaningless to us. It's in certain circumstances, it leads to the idea of an infinity. For example, when we looked at the behavior of the function, let's get this straight on our board. We looked at the function 1 over x. And we said f of x equals 1 over x. And as we plot that on an xy, as we approach 0 from above, if we had x and we had point 0.1, 0.1, 1, and 10. Let's say this is, let's expand our axis a little bit. Whoops, boy, that's awful. Let's redraw the axes. Problem is I don't have very steady hands. Okay, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that's 10. Here's 1. 0.1 would be right in here. Somewhere there. 0.01 even in between. Well, that's 0.1. And we have 1 over x. And this is 100. This is 10. This is 1. And this is 1/10, or 0.1. So we have 1, 2, 3, 4, 5, and so on. Well, this one way there, it's way up at the top off the board. 0.1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's somewhere up in here. That's let's say that's 10. And then down here, this is 1. And then over here, it's 0.1. And so we end up with a very steeply behaving curve like that. Okay? And then if we had the negative side, we'd have a curve that would look the same on that side. And so we have a function that looks like that. And this me not being the artistic person. So what happens in the realm where we have x0, because it can take on this function can take on every value except 1. It's defined at every value x except x equals 0. Because when you have x is 0, then this thing blows up to infinity. And it doesn't make sense. So you can approach 0 from two different sides, from the right side or the left side, and you go either to negative infinity towards it, or you go towards positive infinity. So from the right, you're approaching 0 in this direction, and it goes up, and over here, you're approaching 0 from the left. This is right, and this is left, and this goes to negative infinity to positive infinity as it approaches 0. But x can never be 0 because it's undefined at 0. So we have a problem with functions like that. And there are a multitude of functions that lead to enigmas like that. Well, when we talk about the limits and the behavior at certain functions, for example, let's say f of x equals x squared plus 2 over x minus 1. What happens when x approaches 1? Well, then x minus 1 approaches 0, and we have f of x getting really big again, going towards infinity. So we have problems with many functions that are indeterminate at certain values. And for example, x squared minus 1, x minus 1, and as x approaches 1, the denominator approaches 0, and this approaches 0, and you have 0 over 0. And that's indeterminate also. So we have a lot more functions, really, that we can't say what their behavior is at a particular value. But that doesn't mean that a limit doesn't exist. And if we knew calculus, we can define those limits. In fact, the limit as x approaches 1 for x squared minus plus 2 over x minus 1 happens to be 2. But you wouldn't know how I got that, and I can't factor that out. In fact, I think and this would be x squared minus 2 square root of 2x plus 2. So we got x squared plus 2 minus 2 square root of 2x. So we say that we've got, if we do this squaring, we have x minus square root of 2 squared plus 2 square root of 2x and x minus 1. But that doesn't help us any. It makes, there's nothing we can do to make this function something that we can work with in order to find the limit. Calculus gives us the ability to do that, though, but we haven't learned calculus yet. But there are many functions that we can work with, and we'll take a look at a number of them, and we'll take a look at their limits. Okay, so for, let's say, a function f of x equals x squared minus 2x plus 1 over x squared minus 1. Well, if we do a little factoring, we could say, and what we want to know is that in the limit as x approaches 1, what is the limit of f of x? Well, we see that if we just take this function, as x goes to 1, that denominator goes to 0, and we have a problem there with that. This is 1 minus 2 plus 1. So we end up with 0 divided by 0, and that is a problem. So is there a limit to this? Well, we can do some factoring. The limit of x as it goes to 1, whoops, didn't draw a very good one there, as it goes to 1 of x squared minus 2. Well, let's see, what is x squared? Let's see, x minus 1 times x minus 1. That's x squared minus 2x plus 1. So if we factor that, we have x minus 1 times x minus 1 over, and x squared minus 1 is equal to x minus 1 times x plus 1. And that's x squared minus x plus x minus 1. So that's x squared minus 1. So this is about the only area where factoring actually becomes useful. So this denominator becomes x minus 1 times x plus 1. And look at that. We can cross that out, and we can say that this is the limit as x approaches 1 of x minus 1 over x plus 1. So this is no longer 0 down here. In fact, that's 1 minus 1 and 1 plus 1, which is 0 over 2 equals 0. So in the limit, as x goes to 1 for x squared minus 2x plus 1 over x squared minus 1, the limit is 0. So we have a distinct limit, even though in the strict sense, if we just use the function as it exists, it would be indeterminate. So if we do a little factoring, there are functions that we can find the limits for. And if you looked at x squared minus 2x plus 1, and we had x is minus 2, minus 1, 0, 1, 2, 3, and we got x squared minus 2x plus 1, so that's 4 plus 4 plus 1 equals 9. This is 1 minus 2 plus 2 plus 1 equals, that's 4. This one is 1. 1 minus 2 plus 1, so we have minus 2. 4 minus 4 plus 1 equals 1. And 3, that's 9. Minus 6 plus 1, that's 3 plus 1 is 4. So if we plotted that on an xy coordinate system, we have, let's just bring that out. We got 1, 2, 3, 4. Let's do minus 3 also. Minus 3, that's 9. 9 plus 6 plus 1, that's 16. So minus 3, we have 16. Let's do this. 2, 4, 6, 8, 10, 12, 14, 16. All right, so at minus 3, we got 16. Oh, this is minus 3. I'm sorry. Minus 3, that is 16 there, somewhere around there. And at minus 2, we got 9, 2, 4, 6, 8, 9. At minus 1, we have 4, 2, 4, minus 1. And at 0, it is 1. 1, 2, 3, 4, 5. Okay. At 1, it's minus 2. Minus 2. At 2, it's 1. 1, 2, so there. And 3, we got 4. So we end up with a pretty steep parabola like that. And the zeros for this function are x minus 1 and x minus 1. So x, the function is 0 at x is 1. And 0 at x is 1, 1. Yep, that's 0. All right. But being a square, it should have 2 zeros. So we should have let's see, x squared minus 2x plus 1. It should be a parabola. And let's take a look at this. So x is minus 3, minus 2, minus 1, 0, 1, 2, 3. This is 9 plus 6 plus 1. We got 4 plus 4 plus 1. We got 1 plus 2 plus 1. We got 1. We got 1 minus 2 plus 1. We got 4 minus 4 plus 1. We got 9 minus 4 plus 1. 5, let's see, 25 minus 10 plus 1. So this is 16. This is 9. This is 4. This is 1. This is 0. This is 1. This is 6. And that is 15, 16. There should be 2 zeros there, x minus 1 and x minus 1. So it's at x equals 1 is the only time in which the function is 0. And so it never actually crosses the line, so it's a minimum at 0. So we have at 1, we got a 0. At 0, we got a 1, and it goes like this. So that's our parabola. And I'm not a very good drawer. And it just, this is our minimum here. But other functions will have 2 points where it crosses there and there, or there or there. There are always 2 solutions, and in this particular case, both solutions happen to be 1. So there goes my artistic. So we had this. So we had x equals minus 3, minus 2, minus 1, 0, 1, 2, 3, x squared minus 2x plus 1. This is 9. 9 plus 6 plus 1. This is 4 plus 4 plus 1. This is 1 plus 2 plus 1. This is 1. This is 0. This is 4 minus 4 plus 1. This is 9 minus 6 plus 1. And this is 16 minus 8 plus 1. And so this is equal to, all right, this is 16. This is 9, 4, 1, 0, 1, 10, 4, and this is 8, 9. Okay, so we have our symmetry there. This 5 would be 16. And then x minus 1, we have minus 4, minus 3, minus 2, minus 1, and this is 0. And this is 1, 2, 3, 4. Okay, and this is x squared minus 2x plus 1. So this is minus 4 minus 3 minus minus 2. This is minus 1 and 0, 0. So this is undefined. And then we have 1, 2, let's see, 1, 2, 3, and this is 4. So when we look at the function, x squared minus 2x plus 1 over x minus 1, we have minus 4 minus 3 minus 2 minus 1, 0 over 0, 1, 2, 3, 4. And if we wanted to plot that, we have, well, let's find some room here. That and that. Okay. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4. And 1, 2, 3, 4. So at minus 3, it's minus 4. So we got there. Minus 2 is minus 3. So there, minus there. Minus 1 is 2. At 0, it's minus 1. And here it's undefined. So, but here we pick up again. At 2, we have 1. At 2, we have 1. At 3, we have 2. 4, we have 3. And at 5, we have 4. So we have a line with a break right there. And we have 0 over 0 at this point. But having done our factors, we know that our limit as x goes to 1 of x minus 1 times x minus 1 over x minus 1 equals 0. And that's our limit. So the function has a limit that we're approaching, but it never gets to that limit. It just approaches that limit as we get closer and closer. So there's some continuity to the line. This ratio plots a line. And even though we don't really get to 0, our limit is 0. And that is often the case with functions where we have indeterminate limits. We'll find that in the vicinity of where the function is undefined, 0 after 0, or 0 divided by 0, the value it takes on would complete the function if it could take on that value. So just some interesting things about limits. I'm sorry about some of my lack of artistic ability. So let's take a look, but I do think graphing does help give you some kind of an idea or perspective. So let's take a look at a couple of other functions. Let's say f of x is equal to 2 minus the square root of x over, what is that, 4 minus x. And we say, what is the limit as x approaches 4 of 2 minus square root of x on 4 minus x? Well, if we just plugged in 4 into x, we'd have 2 minus the square root of 4, and 4 minus 4, again we have 0 over 0, another indeterminate one, so that creates a problem. So if we do some factoring here, we could take a look at that and we could say 2 minus square root of x times 2 plus the square root of x, and then we have 4 minus 2 square root of x plus 2 square root of x minus x. So that's equal to 4 minus x. So we can say that this is 2 minus square root of x over 2 minus square root of x times 2 plus the square root of x. And now we have a totally different situation. By factoring, these cross out, and we have the limit as x goes to 4 of 1 over 2 plus the square root of x, which equals 1 over 2 plus 2 equals 1/4. So rather than 0 over 0, we have a distinct limit as x approaches 4. But again, we can't, given the particular function that we can't have 4, because then it's an indeterminate ratio of 0 divided by 0. Okay, so we're going to take a look at this next one, which is f of x equals x squared minus 9 over x squared minus 2x plus 2x minus 3. Okay, so the upper one can be factored. So we got x plus 3 times x minus 3. And that would give you x squared minus 9. Now the bottom one also could be factored. So x squared plus 2x minus 3. So let's say x plus 3 and x minus 1. So we got x squared plus 3x minus x minus 3. That's x squared plus 2x minus 3. So we got this, x plus 3 and x minus 1. And what they wanted was the limit as x goes to 1. So we have here, we have 1 minus 9 over 1 plus 2 minus 3, and that's minus 8 over 0. So that makes it difficult looking at that function just as it is, does factoring help us any? We have the limit as x goes to 1 of x minus 3 and x minus 1. Well, it looks like it still creates a problem for us because this goes to 0 as x goes to 1. So that still creates a problem for us, even though we're able to factor it and reduce it down a little bit. It still gives us a problem at the value x equals 1. So let's see if I actually wrote that problem down correctly. I guess I did. Now, is there anything that we can do? This is solvable because, let's see, is this solvable? Yeah, it is. It is solvable because if you applied what they call L'Hopital's rule, it will give you a result. Is there anything that we can do here to factor this out any that might work in our behalf? Let's see. I don't see anything except L'Hopital's rule. And if we did L'Hopital's rule, we'd end up with 1 over 1, which is 1. So there is a limit. But in this case, this is one of those circumstances where we would have to use a calculus trick in order to find the limit. But there are many functions that you can find limits. I got a nice book here that can help us with some functions. We'll look up limits, and they will give us some. Now, this is a book that is actually geometry and trigonometry for calculus. So this is a pre-calculus course, and it has specific functions that are designed for, here we go, limits approaching 0, 359. Page 359. Okay. And they give us some problems here where we are looking for limits. Okay, so here's another problem. What if the function we're looking at is f of x equals x squared minus 1 over x minus 1. And if we wanted to take a look at that as x approaches 1 of x squared minus 1 over x minus 1, we'd end up with 0 over 0. And that, again, is an indeterminate result. It's something that's meaningless. We can't say anything about that. But we can take a look at this function and we can see it's factorable. So if we take the limit of x goes to 1 of the top function is x minus 1 times x plus, x plus 1 over x minus 1. We see that these factor out, and we have limit as x goes to 1 of x plus 1, and that equals to 2. Now, if I applied L'Hopital's rule, I would get the same result. And L'Hopital's rule would give me 2x over 1, and then you'd plug in 1, so that's 2 over 1, which is equal to 2, so they're the same. So L'Hopital's rule is a powerful tool, but again, you don't know how to perform L'Hopital's rule unless you know a little about calculus. But I just don't want you to get worried when you see functions that seem intractable, that appear like there's no solution because you can't find the limit from factoring. There is a methodology that broadens your scope and broadens your ability to be able to solve limits. But it does take some understanding of calculus to do that. Now let's see if they give any more functions here where we can take a look at limits. Well, I guess not. They have given us a little bit in terms of sequences, but it's not that tremendously important that we are able to do functions. Let's take a look at one more for limits. Let's say we have f of x equals x squared minus 9 over, let's say, x squared plus 2x, let's say minus 2x plus 3. Let's say, and x is let's look at this. Let's take a look at this. Well, they give us x squared minus 2x plus 3. That would be x plus 3 times x minus 1. But that does not give us, let's see, that's x squared plus 3x minus 3. That's x squared plus 2x minus 3. And let's see now what happens if this is x plus 1, or x plus 3 times x minus 1. Okay, x squared plus 2x minus 3. All right. What happens if we approach x equals 1? So limit as x goes to 1. So that's 1 plus 2 minus 3. Yeah, we got a problem there, you see. Now, with this function, we have x squared minus 9. And if we have 1, right, x squared plus 2x minus 3, we have 1 minus 9 over 1 plus 2 minus 3, and that's equal to negative 8 over 0. But if we do some factoring, I don't know if that helps us any. This is x minus 3 times x plus 3. That would be x minus 3 times x plus 1. All right, so that's x, maybe that, x minus 2x minus 3. That's the, now that's problematic. So this, I factored that wrong. This is x plus 3 times x minus 1. So that's x squared plus 2x minus 3. And so these factor out, and we still have limit as x goes to 1 of x minus 3 over x minus 1. And that gives us 0 over minus 2. And that still gives us a problem. It doesn't, it's not defined there. So we have a problem with that. But what if we had x goes to minus 3, so let's see, minus 3, that's 9, minus 6, minus 3. So let's take a look at this one. This is a good example. Now, as it goes to 1, we can't find the limit without using L'Hopital's rule. But what if we said that this, as x goes to 3, of x squared minus 9 over x squared minus 2x plus 2x minus 3. Well, we have 9, let's see, minus 2x. Okay, so this is 9. This is minus 6, minus 3, and that's 0. Here we have 9 minus 9, so we have a 0 over 0 situation as we approach 3. But this one we can factor out. Even though it's indeterminate at this point, we can factor out the numerator and the denominator. So this is x plus 3, x minus 3, and this is x minus 3, x plus 1. Okay, so that's x squared minus 2x minus 3. So that's the proper factors. And this cancels out. And we have the limit as x goes to 3 from x plus 3 to x plus 1. And that's equal to 3 plus 3 over 3 plus 1. That's 6/4. So we do have a value for that one. Even though in this condition we have 9 minus 9, we've got 9 minus 6 minus 3 equals 0 divided by 0, which is nonsense. You can't have that. So by factoring, we were able to solve this. And there are a lot of these functions that you're able to factor and find the limit. And there are a lot where you're not able to. And that's where the calculus is going to be helpful, because it expands our ability to do limits. But why are we even concerned with limits? Well, we're concerned with limits because in certain functions we're interested. I'm not too good with this. Let's take a look at this. Maybe I can use this and draw it more straight. With certain functions, we're able to, oops, that's x, this is y. Let's say we had some function f of x. We don't know what that is, but we wanted to know, let's say, what the slope is at that point. And we can see that as this curve here moves along the x-axis, that its slope changes. Here the slope is like that. Over here the slope is like that. Over here it's steeper. And so this function's slope changes depending on where on the curve you're looking at the slope. And so it's not a constant. It changes. And we want to know what that slope is at some given point in the curve. And so how do we do that? And we can do that by looking at limits. And what is a slope anyway? A slope is a rate of change. So here, if we look at a line, a straight line, let's say we got y equals mx plus b, all right? And b is the intercept and m is the slope of the line. So we have x1 or x2, and we have x1, and we have y2 and y1, y2 and y1. So the slope is the difference, the change in the height over the change in x. So m equals the change, and by the way, that little delta sign means the change or the difference. That's all that means. It's nothing intimidating or weird or special. It just means the change in y over the change in x. And that, remember, is the tangent. Remember in trigonometry, the change in the slope or the change in the y over x is the tangent of theta. So the rate of change, again, we see tangents coming up. The rate of change of the function f of x equals y equals mx plus b. And so here the change in y is y2 minus y1 over x2 over minus x1. And that happens to be the slope of this function. Now that's a linear function. That's just a line. That isn't anything that's super difficult. But with other functions, it's not so straightforward because those functions have a different rate of change as you move along the curve. So basically, if you're talking about a linear function, you're talking about a constant rate of change. No matter where you look on the line, that rate of change is always going to be the same, no matter where you are. That ratio is always going to be the same. So let's say this is 1, 1, and 2, 2, and delta y2 over delta x2 is always going to be the same of delta y1 over delta x1. Will always be the same for a line, no matter how big the triangle. So that is just peculiar to straight lines. For other curves where you got a change in the rate, you got a variance in the rate of change. Here, for example, this tangent is not the same as this tangent. So you got a slope over here that's like that, and you got a slope up here that's like that. So how do you find the slope at any given point? Well, you can pick a point, an arbitrary point, and you can pick a slope here, but you don't. This is just an approximation. It's not very close because the size of the triangle makes it so that we miss a portion of the curve. So what are we going to do? Well, what if we made this a little smaller? Well, then our approximation is closer. It's not exactly the same, but it does get closer. And as we make that triangle smaller and smaller and smaller, we're getting closer and closer and closer to that actual slope for that given point. And eventually, when we make this infinitely small, when we make that change in y and change in x very, very small, as we approach 0, we're looking at a limit. And that's the point. We're looking at the limit as the change in y over the change in x becomes small. So as delta x goes towards 0, delta y over delta x becomes the slope. So we're going to look at that a little bit more closely, because that gives us what we call the derivative of the point of interest along the curve. And that derivative happens just to be the tangent line at that point, exactly the tangent line at that point on the curve. And so we'll be looking at that a little bit more closely, and how you can derive derivatives from any given function. So that's why limits are important. So we'll take a look at that a little bit more closely next time, and we'll have better graphics. But basically, that's what we're going to be doing. Is we're going to take a look at how you derive. In fact, that's deriving a derivative is a little bit redundant, because that's what a derivative is. It's a derivation of the slope of a given function at a given point. So that's why they call them derivatives. And then we have integrals, which are another animal altogether. And we'll take a look at that later. But the first thing we're going to do is we're going to take a look at how functions behave, and how to obtain their derivatives. So, and we're going to take a look at it from the way Newton would have looked at it. Newton didn't have the benefit of limits. Nobody really invented limits at that time. He used tables. He used the same idea. He used the same concepts, but he did it in tabular form. And we're going to take a look at how Newton would have calculated a derivative for a function at a given point. And in fact, they probably were using it even before Newton, but that's a little speculative. But the idea of calculating the slope of a curve at a given point is at the heart of derivatives. So anyway, that I hope helps a little understanding, gives you a little bit of an understanding of what a limit is, and how limits are helpful to us in developing derivatives for functions. And once we understand derivative and how it came about, then it becomes very easy for us to actually calculate derivatives. They're not hard at all to calculate. In fact, there are some formulas that we can use that make it very easy for us to come up with an exact derivative. And we'll derive those formulas for you, so that you just don't have to memorize it. You'll understand how those formulas came to be. So until next time, this is Math Man, wishing you all the best, and please stay safe. and follow CDC recommendations for addressing the coronavirus. It certainly helps old timers like me, whom this thing affects the most, and it helps everybody. It helps society and overall. This is a scary thing, this coronavirus. So, this is Mathman wishing you all well.